Hello, everyone, and thank you for joining us today. Welcome to AVO's webinar series. Today's topic is vacuum breaker technology. My name is Ron Spatero, and I'm the marketing manager for AVO Training Institute. And I'll be your moderator for today's presentation and supporting you on technical issues or questions for our presenter. On the right side of your screen, you'll see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will answer the questions during the Q&A segment at the end of the webinar. All attendees are eligible to receive one NETA CTD and one professional development hour. You'll receive your attendance confirmation in an email a few days after the webinar. That email will also include a copy of the PowerPoint presentation and a link to the recorded video of the webinar if you'd like to watch it again or share it with colleagues. Remember, you can ask questions at any time during the presentation, and they will be answered after the webinar ends. Our presenter today is Greg Richmond, AVO instructor and training specialist. Okay, Greg, let's go ahead and get started. Thank you for joining us.
Thanks, Ron. And I want to say that this is my third webinar, and the first two were fairly successful. The first one's pretty good. This one here in particular, as far as a vacuum interrupter is concerned, is going to be something that a lot of people, they tend to kind of get the wrong idea about, or maybe don't fully understand about the true anatomy, all right, the true working principle, and some roundabout information about a vacuum interrupter. All right, so I mentioned vacuum interrupter. I'm going to let you know that that there's a slide that's going to be in here that is a interrupter application slide, I want to say, and it's indicative to different applications toward a vacuum bottle. So I'm referencing a circuit breaker at first. I'm going to let you know exactly, talk about what a circuit breaker is all about, but I want to understand that within this webinar in particular, we're talking about the true bottle and its interrupter itself. I think this is going to be a good one. I think you guys are going to enjoy this. I got a couple of videos in here that I put together for you guys, thanks to some recent classmates. I put a shout out to Western Electric in Sumner, Washington. Thank you for those videos. But our subject and topics that we're going to be discussing today is going to be the anatomy of the bottle. What's the bottle all about? Okay, what are the main components of the bottle itself? The working principle is another subject that we'll be talking about. What happens to that bottle internally when it opens and it closes? All right, what's protecting that bottle from what we like to call unplanned rapid destruction, URD? Okay, what prevents that bottle from erupting under some sort of a load? All right, in the event that something catastrophic happens. We're going to talk about of course, the advantages and disadvantages. There are going to be some pros and cons when it comes to this particular interrupter, all right, meaning positive and negatives out there in the field and whatnot. And of course, applications and testing. Now, I may circulate on this one just a little bit longer than normal because I think that it's critical to understand that testing a vacuum bottle in particular, is very sensitive. So application and testing is important. I've got a few standards for you with this particular slide that I'm going to point out to you, and I want you to take note of them also. And then, of course, with any webinar and with any type of electrical work out there in the field, we'll finish off with safety, because there are some huge safety factors that come into play when we're testing vacuum interrupters. And then, of course, in conclusion, we'll finish it up with a summary. So, like I said, we're going to start out with what the true meaning of a circuit breaker is. Okay, so a lot of times the vacuum bottle is referenced directly to a circuit breaker. Okay, but so we'll talk about it first. So what is a circuit breaker anyways? Well, first of all, it's either automatic or manual. Okay, basically what it does is it does what it's told. It opens and it closes either automatic or manually. A lot in my classes, I like to refer to these circuit breakers kind of like as the Rock, right? Dwayne Johnson. And I'm not beating him down or anything, so if he's on the webinar listening, don't come get me, boss. But either way, they're like the Rock. It does what it's told. It's just a big piece of equipment. It's rated for a particular amount of voltage. It's rated for a particular amount of surge and current. It's got a BIL. It's got a medium. All right, it's got a way of extinguishing the arc, of course, the medium. It's rated for a particular nominal voltage, and it just opens and it closes. That's it. That's it. But in this case here, we're going to talk about next the vacuum interrupter involved with the circuit breaker. But ultimately, the circuit breaker is designed to open or close under load without damaging itself. That's it. It does what it's told. It's got some sort of overcurrent protected device, and it's being controlled by a relay of some sort that's going to open that circuit breaker up so that catastrophic failure doesn't occur inside of our substations or our MCCs. It's designed to carry the full load current. That's our main contacts. And so I'm touching lightly on main contacts right now, and a few slides down, we'll talk a little bit about how to test those main contacts, because I think that that's critical. Testing those main contacts is critical. So it's designed to carry that full load current, and it's rated at plus or minus, greater than 5% nominal voltage. Okay, it interrupts the flow of the fault. It interrupts the flow after a fault is detected. Okay, it opens up whenever a fault is detected based on our devices that are hooked up to our breakers. Unlike a fuse that must be replaced, a circuit breaker can be reset, which is a good thing, unless there's any damage to this particular breaker, which of course we definitely don't want to be a part of the situation. How about a vacuum? How about a breaker with a vacuum interrupter? So this type of vacuum breaker, of course, let's talk about mediums first. We'll get into that in just a second, but provides the same service as any other medium voltage or high voltage circuit breaker. The vacuum is used as the arc quenching medium. So with mediums, we've got several different styles out there we can come up with. Our focus today with this webinar is going to be a vacuum interrupter, a vacuum bottle. Some other out there in the market, of course, is going to be an oil type medium in our circuit breakers. We could have a SF6 as a medium, or of course an air is another one that we could have as well. We may get into webinars later on down the line to kind of break down an OCB, break down your SF6 mediums and with breakers and whatnot, and then of course your air breakers as well. But either way, when the contacts are open in a vacuum, the interruption occurs at first current zero. I'm going to circulate on that one a little bit in just a second, but with dielectric strength between the contacts building up at a rate thousands times higher than normal circuit breaker. Okay, so that first current zero, that's what we want to, the interruption at first current zero, meaning that the highest value that breaker, that interrupter bottle is going to have at it, it's going to interrupt it at that first current zero. The last one down there is it talks about the degree of vacuum is in the range from a 10 to the minus 7 and a 10 to the minus 4. This is called a torr. All right, and this is what the value is of pressure internally with that interrupter. The anatomy of the bottle, this is simple, but I think that this has got to be one of the most important pieces, because understanding how this bottle works is critical. Vacuum interrupter technology was first introduced in the year 1960, but still it is a developing technology. As time goes on, the size of the interrupter has reduced from its early 1960 size, but due to different technical developments in this field of engineering. So there's one thing I want to point out about this slide, okay? And I want to say this, that within this slide, or this presentation, you're probably going to notice that I'm not putting any type of voltages as far as the capability of these interrupters, because there's technologies out there that are exceeding higher voltages, well above medium style voltages when it comes to interrupting technology using a vacuum bottle. So for me to limit this bottle to a certain amount of voltage would be something that is undermining to this bottle. So when I say technology is developing, we're talking into the 500 range and so forth. There's three main pieces of this bottle that we'll talk about. That's our fixed contact, our movable contact, and our interrupter. So the fixed contact, let's get into these main components real quick. You can see that on the right side over there of the picture, we have a fixed terminal on the top portion, a fixed conductor, an arc shield, a movable conductor, and then bellows shield, flange, another flange on the right hand side, a fixed contact, an insulator, bellows, and then of course the movable terminal. So our fixed contact, these are our main pieces. Our fixed contact is going to be the stationary contact. This is what's going to be connected directly to the unit itself. All right, not going to do much. Still going to have a set of contacts on the other side of it. And then we've got our movable contact, which is going to be controlled by a set of linkage systems with whatever we're connected to as far as that body is concerned. Our movable contact, and this is going to this enables the permanent sealing of the vacuum chamber so as to eliminate any possibility of leak. Okay. So this movable contact is obviously going to open and close the contacts based on the stationary in its position, and then it's going to allow that arc to be open. The most important part of this particular portion of this bottle to me is this bellows down on the right hand side. You can see those bellows. They're come in all different shapes and sizes, and I'll show you I got a couple other shots in here of some flexible metallic bellows, and what these flexible metallic bellows do is they allow that movable contact to open and close and still allow that bottle to retain its vacuum. So to me, that's the heart and soul of this bottle. If those bellows fail, then that bottle loses its pressure and air leaks into that bottle, and now we could have catastrophic failure. Another portion that I want to point out on this particular slide here is that arc shield. Okay, that arc shield is critical because when those contacts open up, a generated metallic plasmic ions are going to open and they're going to be created inside that bottle. So we've got metallic ions that are exploding inside of this bottle, and we need to control that generation. So what happens is that arc shield, that outer shield, is protecting that outer portion, that glass or porcelain portion insulator of that bottle itself. So we've got an outer insulator that's going to be made of glass or some sort of a ceramic material, and then we've got a arc shield on the inside that's going to protect that outer insulator portion. And then the metallic bellows, of course, on the inside is going to be play critical to keeping that vacuum in that bottle. And there's one other piece that I want to talk about, and it's not in the slide here, but I'll move on into it though at a later slide. Okay, so a little bit, I already talked a little bit about this, but just to kind of break down a little more about what's going on inside here, we've got the same basic components as far as our contacts, our movable and our fixed contact again. Our set of contacts inside, remember these are a butt contact. We've got flexible metallic bellows as well, and so forth. But looking inside the bottle, the metal vapor condensing shield, which is already what I talked about, prevents the deterioration of internal dielectric strength by preventing metallic vapors falling on the inside surface of the outer envelope. So remember, we've got that giant explosion going on inside, and the lack of air is causing that arc to be quenched. So we need to protect that outer envelope. The contacts allow full load current to flow without interruption. These flexible metallic bellows allow the movable contact to maintain a vacuum within the bottle with opening and closing operations. So just think of that. It's a simple operation, but it's critical to understand what's going on. And when we get into testing of the bottle, we'll get into testing that value of the lack of air inside of that bottle itself, and also testing the outer insulation portion as well. Contact makeup. So I've got on the left-hand side of that picture there, I've got an example of a butt contact, a spiral contact, and then an axial magnetic field contact as well. So these are just different styles of contacts that are usually available inside these bottles. They have high breaking ability, excellent electrical conductivity, small thermal conductivity, okay, thermal relating to heat. Electrical conductivity meaning the makeup of these contacts is generally going to be made of a copper bismuth type of material. Bigger heat capacity and low hot electron emission capability. High breakdown voltage and resistance to electrical corrosion. They're not exposed to the elements. All right, it's strictly going to be something that's going to be contained, and nothing as far as the outside getting in to cause those contacts to erode or corrode. I got a good shot in here of typical failures that you would see on the vacuum bottle, so you'll get to see some real life pictures and stuff. So, resistance to welding, low gas content, especially copper. Vacuum interrupter contact materials are primarily a 50/50 copper chromium alloy. They may be made by welding a copper chrome alloy sheet on the upper and lower contact surfaces over a contact seat made of oxygen-free copper. Contacts inside. So a little bit about what happens internally. Okay, when the contacts are separated due to some abnormal conditions, an arc is struck between the contacts. The arc is produced due to ionization of metal vapors, and depends very much on the material of the contact. So when an arc is struck, we talked a little bit about this already. There is metallic ions, all right, that develop heat and they explode essentially inside of that bottle itself. Butt contacts shaped with slots and ridges or grooves, they help improve their ability to break higher currents. So you can see an example down there on the bottom when those contacts, they kind of work kind of like cross-drilled and slotted rotors on a brake pad. Think about that heat dissipating through those grooves. It kind of works off the same same principle with these contacts as well. Arc current flowing through the shaped contacts generate magnetic forces on the arc column, which cause the arc contact spot to move rapidly over the surface of the contact. This reduces contact wear due to erosion by an arc, which melts the contact metal at the point of contact. Pretty simple and basic design when it comes to contacts and their makeup. The working principle: when the breaker operates, real simple, the moving contact separates from the fixed contact. That's it. The movable contact is the only piece that moves back. The fixed contact stays exactly where it's at. An arc is struck between the contacts. The production of this arc is due to the ionization of metal ions and depends largely on the material of the contacts themselves. Okay? Depending on the size of the contacts, that will determine how much ionization occurs inside that bottle. The arc is quickly extinguished because of the metallic vapors. Electrons and ions produced during the arc are diffused in a short time. Why? Because of the lack of air, and detained by the surfaces of moving and fixed members and condensing shields. There's those condensing shields I was talking about earlier, those metal vapor condensing shields. Those metal vapor condensing shields help to contain those ions, and they help to protect that outer envelope as well. Since vacuum has this is a good thing here. One of the advantages of a vacuum bottle. Since vacuum has a very fast rate of recovery of dielectric strength, the arc extinction in a vacuum breaker should be interrupter occurs with a short contact separation. So that right there, my friends, is kind of like the meat and taters when it comes to the principle behind a vacuum bottle, and its pluses. We'll get into advantages later, but its pluses is that it's high dielectric strength, okay, and its lack of when it comes to extinguishing the arc. When the current decreases, the rate of vapor release decreases, and after current zero, the medium regains its dielectric strength if the vapor density is reduced. So this is a good little video to kind of give you an idea about what's going on inside of a bottle. Remember what we talked about when we talked about the opening of the fixed or movable contact and the release of those metallic ions. You'll see the metal vapor condensing shield in here working, and you'll see that explosion with these contacts. So what I'm gonna do is I'm gonna talk through this video one more time. I always like to show these videos twice. I'm gonna pause it here for just a second, and let me get to where I need to be. So I want to point out these metallic bellows up here that we were referencing to. I also want to talk about this shield as well that protects these contacts internally. So you saw the explosion with with the metallic ions when those contacts open up. There's one more thing that I want to point out, and that's this static ring on the outside of this bottle. We'll get into this static ring on the outside, but I want to point out that it is connected to these to this vapor condensing shield as well. So keep that in mind. You can barely see this metallic ring that goes all the way around the outer envelope of this bottle. So keep that in mind. And the contacts open up. You can see that explosion of metallic ions. Now think about this whenever this happens here. Now we've got a explosion of metallic ions, okay, and static charges are going to build up on this inside condensing shield. So it's critical when we're testing that we discharge this outer ring on this bottle in particular. A lot of guys don't always know that. Now I picked that up along the way here recently, that this is a critical item to think about, that this is this ring here, this outer ring in this interrupter can develop a charge, a capacitive charge. So we want to make sure we discharge that. All right, moving on. So under some circumstances, the vacuum interrupter can force the current in the current to zero before a natural zero in an alternating current circuit. Okay, under some circumstances, the vacuum interrupter can force the current in the current to zero before natural zero in an alternating current circuit if the interrupter operation vacuum is not correct. All right. If the interrupter operation vacuum is not correct in regards to AC voltage waveform, when we talk about a waveform, we're talking about a positive AC back down to zero, and then a negative AC strike. Okay. When the arc is extinguished but the contacts are still moving and ionization has not yet dissipated in the interrupter, the voltage may exceed the gap's withstand voltage. This can reignite the arc, causing abrupt transient currents. Okay, so we're talking here indirectly to the vacuum not being correct. All right, meaning that if this vacuum, when we're talking about testing these bottles, we're looking for this. We're looking for the vacuum internally not being correct, because we could have a restrike inside that bottle, causing it to fail. Vacuum interrupter manufacturers address these concerns by selecting contact materials and designs to minimize any type of current chopping. To protect equipment from overvoltage, vacuum switchgears usually include surge arresters, and that's another subject itself, some sort of a voltage surge arrestor in line with our equipment. So restriking is critical when it comes to making sure that we test these bottles to make sure that the internal vacuum is correct, so we don't have this chopping and restriking. All right, so we talked a little bit about the working principle, the anatomy of the bottle. I really like that video on that shows the internal working of the vacuum bottle itself. A little bit about the components when it comes to the movable contacts, the fixed contact, and the actual outside interrupter. Let's get into some advantages and disadvantages when it comes to these bottles. I've already said this before, and I'll tell you again, this is a simple construction. There's not a lot going on, but it's complex, but it's a simple build. A vacuum offers the utmost insulating strength, so it has extreme superior arc quenching properties than any other medium. All right. All we have to worry about is the lack of air internally with this bottle, and that's it. So when it comes to arc quenching, that's ultimately what the goal is at the end of the day. We want to be able to open that breaker up, or that piece of equipment, that interrupter, without any type of damage. But when the dude goes, it's gone. The vacuum circuit breaker has a long life. These vacuum bottles tend to last around 20 to 30 years. Okay, some of these bottles are good for 10,000, 15,000 operations. All right. Unlike old circuit breakers or air blast circuit breakers, the explosion of a vacuum circuit breaker, vacuum interrupter, is avoided. This enhances the safety of the operating personnel. It's quiet, all right. It's maintenance free, almost maintenance free. There are some tests that we need to perform on this interrupter, and we'll get into that a little bit later. The vacuum circuit breaker, vacuum interrupter is fast in operation, so ideal for fault clearing. Circuit breakers, interrupters is suitable for repeated operation. No exhaust of gas to the atmosphere and noiseless operation, meaning that there's no spent gases. We don't have to worry about testing any type of oil, OIL oil. We don't have to worry about doing any type of cleaning, no arcing contacts or intermediate contacts or anything like that. Its disadvantages, okay, of course. The main disadvantage of the interrupter is that it is uneconomical, typically at voltages exceeding 38 kV, and we're talking directly about a circuit breaker. All right, the MCC circuit breakers, the medium voltage, 38K is around where we want to kind of be. Like I said, there are some that are branching out a little higher. The cost of the breaker becomes excessive at higher voltages. Typically, SF6 is what's going to be used as far as anything above 38 kV. It's more 38 kV. It's a little more economical, and it's able to withstand those higher voltages. This is due to the fact that at higher voltages, more than two numbers of the circuit breaker are required to be connected in series. That's in reference to a vacuum circuit breaker. Moreover, the vacuum circuit breaker's production is uneconomical if produced in small quantities. So I've got some examples on the right-hand side of some different types of applications when it comes to an interrupter. All right, obviously with some of the discussion that we've had today a little bit, we've talked a little bit about circuit breakers. This is an indoor type circuit breaker with a vacuum bottle. Outdoor circuit breakers, okay, you can almost see the arresters on top up there in line. They all work off the same principle. Reclosers is another one. A lot of companies are going to be retrofitting with reclosers with small vacuum bottles internally. I've seen a few of those along the way. Load break switches with vacuum bottles in line with the medium voltage contactors. These are the smaller bottles, generally about 3 or 4 inches, maybe about 4 or 5 inches in length. Low voltage contactors is another one. Generator breakers, tap changers. Okay, we could have no load tap changers mounted on the outside with small bottles internally that help with that transition. And railway breakers is another one also. So kind of give you an idea about what you could see out there in the field with interrupters and applications. A vacuum interrupter is recognized as the most reliable current interruption technology. Okay, it requires minimum maintenance compared to other technologies. This technology is mainly suitable for medium voltage type application. Higher voltage technologies has been developed but is commercially not practical in some applications. All right, so this is a good one. You've got some issues with loss of vacuum on the board. We've got mechanical and erosion to kind of give you an idea of some causes of failure. Loss of vacuum could cause a catastrophic failure. This one on the top up there on the left is kind of looks like there was a fire involved in here. Loss of vacuum on the middle picture with an explosion that could have occurred. And likewise on the right hand side, you can see those poles are damaged, and that outer shell is totally gone on that one. So kind of give you an idea of some issues with loss of vacuum. Hopefully nobody's around when that happens during testing, especially. So mechanical failures. Okay, you could have the bottle itself could fail with some broken pieces along the way. With erosion, we could have contacts that could be irreparable, opening and closing, chopping going on with these contacts, causing these contacts to fail, and internally. So just kind of give you an idea of some main failures that you come across with the interrupter. All right, we're going to get into testing a little bit. Okay, so testing preparations is key. Okay, we talk about testing. We talked a lot about the working principle and whatnot with the bottle. We talked a little bit about its makeup and gave a little video about how it works internally. Testing is critical here. We need to make sure that we get all of our tools correct, all right? PPE and testing equipment. Have the right type of equipment for the right job. Make sure that your equipment has been calibrated. Preparing the tools. If you need to have any type of arc flash or shock assessment along with a hazardous work permit, make that happen. Follow NFPA 70E down on the bottom down there. They're going to give you all of that information when it comes to a flash and a shock assessment when we're isolating our equipment. Have all the proper documentation, meaning that any type of recording that you're going to be doing on your testing with your equipment needs to be followed correctly. Testing sequences is good as well, making sure that you test the same way. I like to take a lot of pictures when we test out there in the field so that it becomes redundant in case somebody takes my spot. Then they're able to go in there and they know exactly where I was at. Plan for any type of hiccups. All right, anything that can go wrong will go wrong. Make sure that you plan for those correctly, and if anything happens, stop what you're doing. Okay, because get that gut feeling and understand it. Understand the equipment's operation. Know how to work the equipment. All right, know how to hit that emergency stop where it's at. Safety interlocks are important. Isolate the equipment from your switch gear, obviously. Get it out of the way. Isolate the equipment. Establish a safe working condition. This is good to know. Follow Article 120 in the NFPA 70E. Talks directly about safe working conditions. Lockout, tagout, also 120 in NFPA 70E talks about is all about lockout, tagout. De-energize whatever may be needed. Keep in mind that some of these breakers are going to have a test position, a disconnect, and a connect position. When we're testing these breakers, as found and as left according to NETA and some manufacturer's documentations, we need to make sure that we rack that breaker or pull that piece of equipment all the way out of where it's at. Discharge and ground, I talked a little bit about that. Stored, any capacitive charges that may be stored, we need to make sure we discharge and ground before we put our hands on that equipment. Barricade. Make sure that whenever we're testing that we set up an area clear and free of any persons that may not be qualified to enter into our testing area. We need to make sure that we keep those bad guys out and the good guys in, and while we're doing any type of testing. Now we'll get directly into testing the apparatus. So I mentioned earlier that following strict manufacturer specifications is critical. At AVO, we teach maintenance and safety. A lot of times, we talk about NETA a lot. We teach to a NETA standard, but first and foremost, manufacturer specifications is critical. Get into those books. I recommend you to get in there and highlight your equipment when it comes to testing as far as vacuum bottle is concerned. Any contact erosion indicators, all these different companies are all going to have different ways of testing for contact erosion. So get into those books. Some companies may recommend a reference line on the moving shaft, some sort of an indicator. It could be a line around the bottle shaft, the movable shaft itself. It could be a scribed or a paint marker. Some will reference a fixed point on the piece of equipment. Some breakers will also have a disc type wrapped around the movable shaft that will line up with another piece on the apparatus that you're testing, and that's going to show any type of contact travel and wear and whatnot. So get into your books and find out. So contact erosion and contact resistance. ANSI standard states that we have to use a minimum of 100 amp source. Okay. And this is going to tell us how well the contacts make internally. Since this is an interrupter vacuum bottle, we can't physically see those contacts. Therefore, we have to use a low resistive ohm meter in order to tell how well those contacts makes, and it's read in a resistive value. Check in your manufacturer's books and see what that value is going to be. A lot of companies will recommend a minimum resistive value of such and such ohms. Okay. Insulation resistance. All right, this is testing the integrity of the insulation between insulation to ground and between all phases. We want to know what type of leakage current is going from our induced voltage, all right? And we are reading that leakage current to ground between each phases and ground, of course. Okay, so this is an important test. Not as destructive as a vacuum bottle integrity test is, but it's still a good reference in the insulation quality between phases and ground. And then the last test down there is going to be this vacuum bottle integrity test. This test here is the most important test when it comes to testing the interrupter. It's tested with an overvoltage withstand, also known as a high pot tester. Okay, this tests the integrity of the bottle, how well that bottle, the internals of that bottle, is able to hold a vacuum. Okay, I'm going to get into some other testing technologies and whatnot, but this is going to be a DC type test. Now, this test right here I want to talk directly about, and I want to say that it's critical for you to follow your manufacturer's specifications. And so your manufacturer specifications are going to talk directly about an AC test more often than a DC test. I know the haters out there are already throwing bricks at me, but either way, 9 times out of 10, your manufacturer specs are going to tell you that to perform a vacuum bottle integrity test needs to be done with an AC tester. Okay, I get it. And then, of course, at the very last page, on the very bottom, they're going to give you about an inch and a half worth of line, and it's going to say, in case you don't have an AC tester, use a DC tester. So that's where the square root of 2 comes into play when it comes to converting an AC test to a DC test. So use the square root of 2 to come up with the proper DC test voltage when it comes to an AC test voltage that's been supplied by the manufacturer. Overvoltage withstand tester, okay, also the last one down there, testing integrity of the insulation at a higher voltage. All right, the differences between vacuum bottle integrity and the overvoltage withstand test is that one, the contacts are open, the other, the contacts are closed. So this is all manufacturer specifications. I tried to beat that up as much as possible. I wanted that to be kind of like the most important slide when it comes to testing the apparatus, because first and foremost, this is critical to follow the application that the manufacturer has to say. More on testing the apparatus. If the manufacturer's literature is not available, use NETA MTS, International Electrical Testing Association. MTS stands for Maintenance and Testing Standards. So like I told you before, AVO, we teach maintenance and safety. So this is the standard that we follow is NETA MTS. So when we get neck deep into NETA whenever we're talking in our classes and whatnot, but like I said, with interrupters, I have my guys go right into the manufacturer's books. One more thing I wanted to point out to you before I go any further. One of my go-to websites that I use out there, if I can't find any manufacturer's docs on a customer or a client's piece of equipment or literature, I use electricalmanuals.net. So just to kind of give you guys a little bit of insight on, found everything from manufacturer's documentation to standards when it comes to commissioning, and from the not commissioning, but all the way to manufacturer's standards on tests on equipment that's before it's even left the shops. So anyways, NETA was developed for the technician to test electrical equipment with specific literature is not available. Understand that NETA is strictly used as a guide for the technician out there for testing equipment. It follows guidance from IEEE, ANSI, and NFPA 70E. So all these different agencies are coming together, these subject matter experts, to put NETA together in a nutshell, okay, to give you an idea of what NETA is all about. NETA gives a sequence of tests. This is important. All right. NETA gives a sequence of tests that are to be followed chronologically, meaning that you're not to proceed to the next test unless the previous test passes. Obviously, you won't want to move to a overvoltage withstand test or a vacuum bottle integrity test if your insulation resistance test fails. That's in a nutshell what that's all about. So chronological is key, and I'm glad that they put that together like that. It's real easy to follow. NETA also provides test voltages at a minimum standard for results with electrical tests. So they also provide a voltage, and along with that testing voltage and sequence, they also give you a value, meaning that, hey, if I test this apparatus at this piece, then this should happen, or this is the type of results I should have. In this case here, testing a vacuum bottle integrity, doing a vacuum bottle integrity test, it's a pass or fail test. It's a go or no go, thumbs up, thumbs down. But in this case here, a lot of times what I'll do is I'll preach and I'll teach that, hey, look, I know with a over voltage withstand tester, it's a pass or fail test, but we can also record leakage current as well. We want to train that leakage current, okay? Because these pieces are man-made and eventually they'll fail. So we want to trend that and make sure that that we're watching that we're watching it and making sure that it's we know when it fails and whatnot. So keep in mind, the next one is going to say that it is a great guide for testing most any electrical apparatus and is used as an industry standard for testing. Don't need to say much on that one. And the second and last one there says, no, I don't get a kickback from Anita. I believe following standards and criteria. Okay, so a little shout out on Anita right there. If you get to the 2015, it's the new one should be coming out next year. So another source for testing is going to be this IEEE 37 gives a lot of good information when it comes to switchgear and apparatus in regards to what IEEE has to say about testing. Magnetron atmospheric condition tester is another one that tests the value of that vacuum internally is another example. And so another one that's is going to be coming up here fairly soon at the end of the slideshow is Megger's version of the atmospheric condition tester in regards to the vacuum bottle. So if you're interested in something like that, we can definitely set you up with some information on how to acquire one of those pieces of equipment. It's less stressful on the equipment when it comes to testing. So here's another video. This video here, I got a couple of these show you some leakage current that's tracking on the outside of these vacuum interrupters. You can see that leakage current. That leakage current that's tracking is actually that little section right there in the middle is the bad portion that's tracking. You can see it actually tracking the ground down there as well. So a lot of times, I'm going to still keep talking. A lot of times with these training classes that we do, don't always get a chance to see what that leakage current looks like, or we don't always get a chance to see what a vacuum bottle when it fails. So I like to kind of put in a situation that could create some sort of a fault to ground, just minimal. And these pieces of equipment are designed to trip out, to open up, to fail, indicating that that there is a problem with that particular circuit. So this is a good simulation. I'd like to use just a little small number, maybe 16 gauge wire, and run that wire from my outside of my insulator to ground, and you can see that leakage current rise with the proportionate rise in voltage. All right, to kind of give you an idea, I wouldn't always recommend that. We control it and it's safe. Lots and lots of safety when it comes to, but a lot of times we're not going to see when it's going to fail. And when it does hit the fan, it's going to hit the fan and it's going to hit it hard. So speaking of safety, kind of finish up on safety. And I've just got a couple minutes left here, but ensure only qualified persons are working with the equipment. And I could probably talk for a good 3 or 4 hours on what 70E's definition is on qualified. I'm not. But an FPA 70E is going to get you neck deep in qualified and what would make a person qualified and not qualified. So make sure that your people know what they're doing. Essentially is what it's all about. Don't get the guy in there who's winging it and so forth. Get somebody in there who knows what's going on and testing this piece of equipment. These bottles are going to could emit some sort of radiation if they do fail at some point in time. They're normally going to be at a higher voltages and whatnot. So make sure that if you are testing these bottles, that you want to keep them about 3 feet away from where you're at. Whenever I'm doing testing on equipment, I like to face my equipment, my apparatus that I'm connected to, but in regards to vacuum bottles, I'll turn them around and face them away from what I like to call the blast point. All right, so that way, if it does fail, it flows the other way away from me. Record and trend these results for future use. Exercise caution with higher voltages. That's critical, okay? Be aware of what's going on around your surroundings. Barricade the test area. Make it quiet. All right, a lot of times, if there's tracking or any insulation that's going to fail or anything that's going to leak to ground, you'll hear it. You'll hear it buzzing, it'll fuzz. You may even see a small arc. Look for leakage current on the overvoltage potential tester. Discharge the equipment tested. That's critical. That capacitive charge that gets stored on these pieces of equipment with the higher voltages, that could kill you. So we want to make sure that we discharge that with a resistor stick first, then send it straight to ground. Remember that little capacitor ring on that bottle too. Observe the condition of the equipment while testing. Be aware of your surroundings. Okay, pay attention to what you're testing is what I'm trying to say. It's going to tell you when it's going to hit the fan. And lastly, and I can't stress this enough, follow strict manufacturer specifications with voltages. Don't play with these voltages. This is critical to make sure that we understand that. When it goes down, it's going to go down. One more thing I want to put in there, follow the testing sequences with manufacturers as well. Some manufacturers are going to recommend testing it for 5 seconds. Some manufacturers are going to recommend testing that bottle for 1 full minute. And lastly, summary to kind of close all this up. It's been a good one. I enjoyed doing this lesson with you. A simple rundown of the anatomy of a bottle, the vacuum interrupter, the working principle behind it, some of the advantages and disadvantages of the bottle itself, the pros and cons. Beat up testing as much as I possibly could because I think that that's where we're going to spend most of our time as technicians. Safety is critical, of course. Making sure that we're doing this correctly, and then of course conclusion. We finished off with our conclusion. So, all right.
All right. Thank you, Greg. Appreciate that presentation. We'd like to show you our training courses, our hands-on circuit breaker training courses at AVO Training Institute. We have an entire suite of breaker training courses. Greg, of course, is one of our instructors. We have the circuit breaker low voltage, medium voltage, molded and insulated case, and also we do the SF6 circuit breaker course. Like for you also to save the date, Tuesday, October 23rd at 1 p.m. to 2 p.m., same time, same place, Central Time. It will be OSHA's safety-related work practices. That's going to be presented by Tom Norwood, one of our senior training specialists and curriculum advisors. Also, we want to mention our Megger vacuum interrupter testing products. You'll see them on your screen there, the bottle integrity tester and the time and travel analysis tester. More information is available on Megger.com under applications if you'd like to know more about these products. All right, it's time for our questions and answers. We've got quite a few questions coming in, Greg, so we'll try to get as many as possible. Also, I'd like to mention, if we don't answer your question, Greg will be sending an email out with the answer to that question. Also, you can get a copy of this recorded video on our website, avotraining.com/webinars. Okay, Greg, let's dig in. Lee wants to know, on a vacuum circuit breaker, is the bill, BIL, lower or higher than an air circuit breaker?
Ooh, that's a good question. That's a real good question. Well, first of all, bill, basic impulse level, breaks down to what's called the amount of voltage that insulation can withstand. Typically, the BIL rating of those breakers is going to be anywhere from 2.5 to 3 times what the nominal voltage is of that breaker. As far as the differences between an air breaker or any other circuit breaker and a vacuum breaker, the bill, to my knowledge, shouldn't be any different because essentially what that is it's just the rating of that insulation of the breaker itself. As far as the poles, when I'm talking about the poles, I'm talking about the portions that separate the conductive movable contact and the conductive fixed contact. That portion is that insulation that we're testing. All that insulation to ground. That's that insulation, the BIL.
Greg, Hector wants to know, why are the contacts shaped in a swirl?
That's funny. So first of all, those contacts are designed. Those contacts are all designed different by different manufacturers. Okay, and we're talking directly about an interrupter. So what that does is like I said, when those contacts open up, all right, those grooves, those swirls allow that current to flow out a little bit easier than just a um, a flat type contact. And some contacts will even have round contacted ends with points on the ends of the contact face as well. Just contact built by different companies allows that current to dissipate quicker and establish current zero.
Cody has a question about one of the images in the webinar. Is there any significance to the pattern apparent on the contact surface?
I think that that's going to be kind of referencing the question that Hector mentioned before. We talked about the contact manufacturer and the contact makeup and the ability to extinguish that current to zero.
Greg, Ronald wants to know, so the condensing shield operates somewhat like a gitter in an old vacuum tube? That's his question.
That's
Reference to slide number 13.
okay. I get to slide number 13. That's a good one. First of all, I'm not familiar with a gitter, okay, but I'm sure it probably works the same as the metal vapor condensing shield. Um, send me this question in an email. I'm kind of curious to see what a gitter is. And as a matter of fact, when I close my computer, I'm going to Google a gitter.
What are the typical contact movement distances?
That's a good question too. We practice a lot of medium voltage breakers, anywhere from a quarter to a 7/8 inch, based on the size of the MV of the breaker and so forth.
Thomas wants to know, is there a way to measure or determine contact erosion caused by continuous or excessive use?
Yes, there's several different ways that you can measure that contact erosion. There's a difference between corrosion and erosion, okay? But we want to measure the erosion. We can measure it by doing an electrical test using a low resistive ohm meter, and essentially all we're doing is we're measuring the resistive value between point A and point B on our breaker or whatever our conductive parts are. The second one that I talked a little bit about is the erosion indicators, okay, that could be, and based on the manufacturer of that bottle is going to give you different ways of measuring that erosion indicator. Like I said, there could be a line around the movable contact, and whenever that movable contact opens up, it goes down. You should see that line on there, obviously. Okay, it should be very visible. And then, of course, when that movable contact goes up and those contacts close, if you can't see that line on that movable contact or on that shaft, then those contacts have eroded. There are some companies out there, okay, with these vacuum interrupter bottles, and so it's critical that you get into those manufacturers' docs and find out. Some will give a specific value when it comes to contact resistance testing, electrical testing. Some will give a resistive or a value on how to measure that contact travel, meaning how wore out those contacts are from constant opening, closing, heat generated, and so forth. All right, but it's critical for you to get into the manufacturer's docs when it comes to measuring that erosion several different ways. Nutshell: contact erosion indicator, electrical testing. Okay.
Dennis has a question about one of the videos. It says the video did not show current swirling. Doesn't the arc swirl so we do not superheat the area of the contact?
All right. So that's just an animation. That's all that is. Just an animation to kind of show what goes on with the movable and fixed contact. And I like to kind of pause that halfway through, the way through to kind of show some key points when it comes to that. So you're right. You're right. It does. I mean, I'm not going to say that it swirls. I'm not going to say that it dissipates equally inside the bottle, but depending on the current generated, will determine how those metallic ions act.
Another question, Greg. Uh, do you use sometimes the RC network in addition to a surge arrestor?
That's a good question. That's a good question. I'll tell you what. Who is this? Let's. Why don't you send this to
Right.
me in a email? That's a little bit out of our scope of training here.
Another question is, since the VCB has so much less mass than other types, air, oil, SF6, are they usually longer lasting for a number of operations?
Usually longer lasting for a number of operations. Well, really what it comes down to is use. All right. How often is that interrupter? We're talking directly here with this question on a vacuum um, circuit breaker. How often does it get used? What is it? What is it protecting? Are there a lot of problems out there as far as it opening and closing under load uh, or under a fault? So each piece of equipment is going to be correlated to what it's protecting and what's out there in the field. Each system's got a history behind it.
Greg, we only have time to squeeze in a couple more questions before the end of the webinar. And one has come in, what as-is tests or tests are required for medium voltage vacuum breakers?
Okay, so that's a good question. So I tell you this much: about 85% of the people that come through my classes are going to be providing some sort of oversight for companies that will be coming in doing testing on equipment. So I bring NETA into the picture a lot, and so one of the things that we do talk about in an as found and an as left test. As is, think about your as found test like this. This is the condition of the equipment prior to maintenance. Okay, the condition of the equipment prior to maintenance, which means that in my mind, and what NETA says as well, is these group of tests are going to be the same test on as found and as left. So prior to any maintenance, okay, before we even touch the insulation, clean it, before we do any checks or anything, and obviously we're limited on this type of interrupter when it comes to adjustments because really there won't be a lot of adjustments. It's a contained unit. So as found and as left in a nutshell are basically going to be about the same tests.
Greg, John wants to give you a compliment with a question. He says that you mentioned an excellent point for discharging the static outside conductor. Could you please describe the preferred method to do that?
That's a good question, John. Of course, safety is critical here. Last time I checked this morning, the theory of electricity is still a theory. Okay, no one can see it. No one can. You can feel it. All right, you can feel those positive and negative particles flowing through your body. But we want to try to mitigate as much contact as possible. So that charged ring on the outside of that bottle there, it's a capacity. It could create a capacitive charge. So a positive way of doing this is with a resistor stick. Okay, and a resistor stick is simple. All it is a piece of PVC piping, and it'll have a set of resistors in series from its first point of contact. The resistors will run from the first point of contact on the stick to the ground connection, which is obviously going to be attached to ground afterwards. So we'll discharge it slowly first, and then we'll hit it with ground afterwards, and that system will be 100% grounded after the fact. Good question, though. I like that question. That's a good one.
We've only got time for a couple more. This one may be a little bit too complicated, but I'll ask it anyway. Could you please talk a little more about the square root of 2 when using a DC hot pot instead of an AC hot pot?
Okay, that's a good question. So,
excuse me, high pot, not hot pot.
All right, well, let me fix one thing first. Okay, we throw that high pot word around. All right, I want people to understand that high pot is a trademark name of a piece of equipment. So when we talk about high potting, we're referring to a piece of equipment. What we want to do is we want to call that type of a test an over voltage withstand test, because that's essentially what we're doing. We're hitting it with an extreme over voltage. So with DC testing and AC testing, there's two total differences there. And so I want to talk about peak voltage, and I want to talk about true RMS voltage. True RMS voltage is different from peak. Peak is that top sine wave at a positive. We go back down to 0 volts, and then we go down to a negative. What we want to do with a DC test is we want to stress it at its peak voltage. So using that AC voltage, all right, we'll multiply that voltage, AC, times the square root of 2, which is 1.414, and that'll give us a good solid number to stress that particular apparatus with a DC voltage. Now, I'm saying this and I'm saying this slightly. I want to make sure that everybody understands out there that we want to make sure we follow these manufacturers' directions when it comes to using this type of voltage. So please get into those books and find out where you need to develop a good solid testing curriculum or state for your equipment that's got a step-by-step procedures, check marks, page numbers, highlight it. Find out exactly what you're all about, because if we don't use the correct voltage, all we're doing is we're stressing that apparatus a little harder than what it's supposed to be and it could fail. And so it could fail on us when we're testing too. So it's critical for you to follow those manufacturer's docs as close as possible.
Greg, it looks like that's all the time we have for the segment. We apologize if we didn't get to your question today. As a reminder, we will email you those answers as we get a chance to, probably in the next few days. And remember, you can watch this entire video on our website, avotraining.com/webinars. You'll also see all the other webinars that we've done through the year, and it's a good resource to go back and review. We hope to see you again at our next webinar, October the 23rd. That's a Tuesday. Same time, same place, 1 p.m. to 2 p.m. Central Time. Thank you for joining us.